2.3, graphing motion. This is actually a big chapter, in my opinion. It looks short, but it's not really that short. You need to sort of understand what's happening between changes in motion. Okay, here's how I'm going to start. I'm going to start with this. I'm going to give you a graph. Let's call this distance D. I don't know, meters, they're the units. Time is typically always at the bottom, right? Let's say seconds. Let's suppose I have a graph like this. 5, 10, 15, 0, 0, 5. Okay, suppose I give you this graph in an exam and I tell you to go from this thing to this thing, the velocity meters per second. So in other words, I want to go from a graph of distance versus time to velocity versus time. How on earth do I do this? Well, all you need to really understand is that velocity or speed, let's say speed in this case, keep it simple. Speed, go back to this expression, is distance divided by time. This is your best friend here. So how do I do this? Well, first things first, you always break up these graphs in terms of segments, in terms of chunks. I can see a chunk here. Let's call this 1. So that's a triangle here. Oops. I can see a rectangle 2, and I can see another triangle 3. That's your first step, break it up into chunks. To go from distance time to speed time, we know that speed is distance divided by time, right? So for this segment here, segment 1, what is the speed? The speed is, I'm going to write it down here. For 1, speed is distance divided by time. Distance is 5, right? It covers 5 meters in 5 seconds. That's the time. So 5 divided by 5, that's 1 meter per second. Time doesn't change. The time axes, always for going between these graphs, leave time the same. So 0, 5, 10, 15. That stays the same. Time doesn't change. What you're really doing is converting between variables, so from distance to speed. So the speed for segment 1 is 5 meters in 5 seconds, which is 1 meter per second. So you label your axes here. 1, 2. 1 is here. It's a flat line. You're going at constant speed, right? Flat line for 5 seconds. Label this as 1. It's a flat line. Why is it a flat line? Well, 1 meter per second is just a number. It's a constant. It's not changing. For 5 seconds, they're moving at 1 meters per second. So it's a flat line, 1 meter per second. And use a different color. For segment 2, this is a rectangle. You have to be careful here. Between 5 and 10, now, segment 2, speed is distance, which is still 5, divided by, I should say, you don't even need to work this out. It's 0. Why is it 0? Think of this conceptually. If you're standing, the straight line means you're basically not moving. 5 meters, at 5 meters you come to a stop. You're not moving. So from 0 to 5 seconds, you're moving up to 5 meters. Then after 5 seconds, you're standing still. So your speed is 0. You're not going nowhere. So you draw a line, vertical line straight down, and that hits the 0 axis. From 5 to 10 seconds, it's 0. Okay, because at 1 meter per second, so you're moving at 1 meter per second for 5 seconds. So after 5 seconds, you drop straight down to 0. Okay, because this is the speed on the x-axis. 0 is here. So it's 0 between 5 and 10 seconds. Between 10 and 15 seconds, your speed goes back up again, but in the opposite direction. Okay, this means you're moving in one direction, then you're moving the opposite direction. So it's like I'm standing here. I move this way, I stop here, then I move back in the opposite direction. So speed for segment 3 is distance divided by time. Distance is 5. If you read the graph up there, 5 divided by the time here, 10 to 15, there's 5 seconds, right? Change in time is 5 seconds. So 5 divided by 5, that's 1 meter per second once again. Okay, I'll say it again. Distance is 5 meters for segment 3. The time is between 10 and 15, 5 seconds. So 1 meter per second, what happens is, because it's a negative gradient, okay, the line's going downwards. For a velocity time graph, you typically get minus plus y and minus y. So you get minus 1, minus 2. Go in the opposite direction. So after standing still, you move at 1 meter per second. So this goes back up to 1. So minus 1 in this case, and a flat line because it's moving at constant speed, right? And it goes back to 0 over here. So you draw a line back to 0, and that's it. I'll explain this again. So to go from distance time to velocity speed time, you use the formula speed is distance divided by time. And you break up the graph into 3 shapes that you can see. There's 2 triangles and 1 rectangle. The first triangle means it's a line going upwards. It's a positive gradient, positive slope in maths. So that means it's going to reach a point 5 meters at 5 seconds. So the speed is 5 meters divided by 5 seconds. That's 1 meter per second. Represent that using a straight line, a flat horizontal line. But after 5 seconds, you're standing still at 5 meters. You're not going nowhere. It's a flat gradient. Okay, that means your speed's going to 0. So you drop from 1 straight down to 0, and that stays 0 from 5 to 10 seconds. Then in segment 3, your distance is 5 meters. That drops down to 0 meters for 5 seconds, between 10 and 15 seconds. So from 0, you go back to 1, straight down to 1 here, minus 1, because it's a minus slope, negative gradient, in the opposite direction. Then you go back up to 0. Now, how do you go from, let's say, speed time to acceleration time? So once again, time stays the same. Acceleration is meters per second squared, if you remember. Looks like that. 0, 1, 2, minus 1, minus 2, because acceleration can be negative as well. That's called deceleration. Okay, and time doesn't change, 5, 10, 15. Now, acceleration by definition is the change in velocity, delta v over delta time. It's how quickly your speed is changing over time. Now, if you look here, it's quite a simple graph, the acceleration graph. I'll tell you why. If you're moving at constant speed here, 1 meter per second, your acceleration is 0, because acceleration by definition is the change in speed. Your speed isn't changing, it's 0. So acceleration is 0 from 0 to 5 seconds, right there. And obviously, so 0 here, 0 meters per second, between 5 and 10 seconds, it's still 0. And between 10 and 15 seconds, it's still 0. So that's your acceleration time graph. It's 0. Your acceleration is 0 because you're moving at constant speed, and you're also stationary here. You're not moving. So that's how you go between graphs. I should also mention, chapter 2.3 talks about distance and displacement. Distance is is the length between 2 points. It's a number. Okay, you can measure it in centimeters, meters, kilometers, no problem. Displacement is distance, but with a direction, and usually means how far you are from your starting point, also known as the origin. Origin, think of maths. The origin is where you begin, usually a graph. So suppose I start at home, I go to school, and then I go back to home. My displacement is 0 because I'm back at my starting point. However, if I'm at home and I go to school and I stay there, let's say the school is, 15 k's away, my displacement is 15 k's. Or suppose I start at home, go directly to school, suppose it's in a straight line, and then I'll go back home and back, let's say I'll go to, the gym, G. The gym is directly opposite, in the direct opposite direction, and the gym is 20 k's away. My displacement in this case will be 20 k's to the left, let's say, or east, or west. Displacement is distance but with a direction. That's displacement. Now, it's usually a straight line distance. Suppose I start here. Another example, I start here. I'll go for a drive in a big loop and I stop here at my destination D. The distance covered is that wiggly line that I just drew here. That's distance D. Displacement is the straight line distance from my starting point to my destination. And we usually give it the symbol S with an arrow on top, or an arrow like that. Displacement is also called a vector. In physics, we have these quantities, scalars and vectors. A scalar is a number. Anything like, I don't know, weight, let's say mass, if you weigh a bag of oranges, temperature, temp, speed, distance, time, these are numbers, right? A vector is is a number with a direction. So suppose I'm pushing a box 10 newtons to the right. That's a vector. Suppose there's a wind coming in at 20 k's per hour northwest. Okay, if I'm flying a plane, there's a wind coming in at 20 k's per hour from the northwest. That's a vector. It's got a number and direction. And displacement is also a vector. So that's that. I will do another video that talks about, that's a brief detour on displacement and distance. I'm going to do another video on how you go between these graphs, but in the reverse direction.